All right, so greetings, everyone. Now I'll talk a bit about a community approach on writing a free embedded controller firmware using reverse engineering. So as an introduction, I'll start. As an introduction, I'll start with my personal use case and situation and explain a bit why I'm motivated to work on this. So first off, my use of technology is essentially I want to use freedom-respecting computers. And actually, I care about this very much because I like to understand how technology works. So I like to have access to the knowledge of how it works. Also because I believe being in control of software instead of being controlled by software is especially important. And because I care about, of course, the community and collaborating together to write nice software, and also security aspects that are not really possible without free software or freedom-respecting computers in general. So I use a lot of different form factors, as most of us do. So desktops, laptops, mobile computers, and also HTPC, so home theater PCs. And really on some of those, I actually run very heavy tasks. So essentially building a kernel or doing full system builds for Android and stuff like that. So I have some requirements there. And my roadmap to actually achieve the use of computers that respect my freedom is to first go with a free system, which is fairly easy to do, running a fully free GNU and Linux operating system, but also go down to the boot of firmware, so essentially coreboot, and also down to the firmware level. So let's take a look at the situation on laptops. Well, what are the available targets now? We have some old Intel x86 laptops which are fully supported by coreboots, so they can actually initialize all the hardware and boot up to the operating system without requiring any blob, which is something pretty nice. Then you have the recent Intel x86 laptops, which have the management engine and all the glory that comes with it. Of course, it's non-free software, and there is also the FSP blob, which is required to initialize hardware, and also some memory initialization code, so MRC usually, that is required for those laptops. So lots of blobs in there, really. Then we have Chrome OS devices. So those are more interesting because they all run coreboot. And of course, they come in different shapes and sizes with different platforms. So you have some Intel platforms which have essentially the same freedom issues as any other Intel x86 laptop, except that, well, it's coreboot, which is, a big improvement, and it has a free embedded controller firmware, which is nice. But we also find some ARM Chromebooks, which are pretty interesting. However, they're interesting because they don't require as many blobs as the Intel x86 platforms. But those are actually much less powerful, and so if I want to run a kernel build on those, it's actually pretty complicated. So the final option there are AMD x86 laptops that we don't hear so much about these days. So let's take a look at those, and in particular, the Lenovo G505S laptop, which is a 15-inch laptop that was released in 2013. It has an AMD Bolton M3 Fusion controller hub and an AMD A-series APU, which are fairly recent and have some pretty decent computing powers. So on this, you can actually run some of the heavy tasks that are part of my requirements. So what's the software freedom status on those? Well, you have coreboot support with AGESA, which is some code that AMD released, which is really not maintainable and not great, but some people still went through and actually ported a laptop using this. So I think the G505S is one of the only examples of AGESA being used for a new port. But it's free software anyway, so it's pretty good. However, it requires an option ROM or a VGA BIOS to initialize the graphics. And there are some CPU microcodes and updates for those. It's not exactly known whether the updates are required for the CPU to work properly. It's, of course, usually a good thing to have these updates to get the CPU running with less bugs and more fixes. but it might still be possible to do without them, since of course they're non-free software. So you have firmwares on really lots of different parts of this laptop. Essentially, on the platform itself, you have the IMC and SMU firmwares, which are integrated, I think, in the South Bridge, and they do some tasks related to power management, essentially. On this generation of AMD, we don't have the platform security processor, which is essentially an implementation of trust zones, which allows executing secure context for special code. So we don't have that. Since it's usually signed, it's a good thing, so we don't have to care about it. You also have firmwares for the USB 3 controller, and just like any laptop, you have a firmware for the embedded controller. So let's take a look at the embedded controller in particular. So why did I decide to take a special focus on this? Well, first of all, it has some very visible user interaction, essentially through LEDs or through buttons and keyboards. And so you might actually want to modify it to, just get it rolling your own way. And something I thought of was, well, why doesn't my laptop just turn on when I open the lid? And this is something I'd want to implement. And of course, to do this, I need free software on the embedded controller. There are also privacy and security implications of using a non-free embedded controller firmware, especially because it's handling the keyboard metrics. So anything you type in there, including all of your passwords, can be recorded by the embedded controller, especially when it has persistent storage to store that information. And it might be able to exfiltrate that data. There have been some investigation about the ThinkPad. I think it was something related to a LED that could be used to blink at a certain rate to just exfiltrate the information. So actually, the embedded controller, even if it's not directly connected to a network connection on its own, it can still find ways to exfiltrate that data. So there are some implications in there. And we might also want to optimize, the power sequencing and stuff that's really low level, but that might still have room for improvement. And it's also a pretty fun kind of thing to learn about and to work with. So I'm actually an electrical engineering student, and so for me this felt like a pretty interesting way to learn about really the insight of how a laptop works at the electrical level. So what's the situation for free software support regarding embedded controller firmwares? Well, we have the Chromium OS EC, which was just mentioned by the previous presentation. So it's free software, it's great. It actually works, and it implements some firmware verification, which is really, really nice. But it only works on the platform supported. Then there was a 2015 Google Summer of Code project by Linksys, who is actually here today, who started reverse engineering the embedded controller firmware of various Lenovo laptops. This is great, but actually it's not the hardware that's on the laptop I'm interested in, so the Lenovo G505S. So let's actually investigate a bit the hardware of this device. So this is just a picture of the board. You can see the embedded controller chip on the bottom right, and actually the Fusion controller HUD on the left side. So we actually have some documentation about this laptop, which is not always the case. So we have full schematics. If you type this into Google, you may or may not find said schematics. I'm not, distributing them or, encouraging anything, but it might just work, just out of randomness. So what's great about it is that we actually have the power sequencing diagram. So the different regulators and power sources that must be enabled and the correct order to enable them. So this is actually really helpful to understand how it works and to write a free software implementation in the end. but we don't have the PCB layout of the board. So the best we can do is just look up the labels that are still printed on the board. So essentially on this, you still get like the name of the components like U3, PQ, 602, stuff like that. So if you just take a close look at your board, you can still match the actual physical components with the schematics. So even without any PCB layout documentation, it's not too painful. So actually about the embedded controller itself, there is also leaked documentation floating on the internet. It's actually much easier to find. So you just type in the chip name and you'll find the data sheets pretty easily. And it's pretty extensive. You have a very precise description of the platform itself, and very specific register descriptions. So stuff that is usually enough to actually get started with writing an embedded controller firmware. And there are also some application notes which are always useful because registers descriptions are nice, but sometimes you need more information than that when it's not that trivial. So some application notes actually do help. So what about the platform itself? So it's an 8051 base CPU. So 8051 is actually a very old microcontroller design. So it runs between 8 and 32 megahertz. It can actually be changed by software. It boots at 8 and can be reclocked up to 32. It's an 8-bit worded processor, which makes actually everything much more painful compiler-wise. But it's like that. And it has a very strange memory layout. If you've worked with an 8051 before, you know what I'm talking about. There are actually 4 distinct memory spaces. So program memory, external memory, internal memory, and SFR, which are special function registers. And there are actually some instructions that allow you to access either one or another part of the memory, depending if you're doing direct addressing or indirect addressing. So you can actually get pretty confused and lost at first. It takes some getting used to, but at the end of the day, this is something that we can work with. And of course, it has all the usual stuff a microcontroller has, so like an interrupt controller, timers, and lots of specific extensions, essentially peripherals and things like this. And it has embedded storage, so 128 kilobyte flash and a 4 kilobyte SRAM. So the flash is used for storing the main firmware, and actually only half of it is addressable within the microcontroller, so you have to play with remapping all the time if your firmware is going to be bigger than 64K, which is actually often the case if you want to write something big and complete. And the SRAM is used for storing some variables, but it's actually more efficient to use just stack in the internal memory. But anyway, many controllers in that platform. So for all the specific protocols you would expect from an embedded controller, so LPC to communicate with a host, SMBus, which is really I2C, and SPI. Of course, some GPIOs, some ADC, DAC, keyboard controller, infrared, and everything to handle like fans, one-wire interface, maybe used for some batteries, I guess, and some more stuff. So you really have like all the controllers you need to do the job of an embedded controller. So let's get starting with development on this. So how to get started? Well, the first step is hardware. We have to start by, finding an entry point to this. And the first thing to get is serial. Well, because if you want to start writing your own free firmware, it's great to have some debugging output. So how do we get serial? Well, just look at the datasheets. So the datasheets of the embedded controller mention a serial port that is accessible from the CPU inside the controller. So that looks good. And it's actually exported to both specific pads, which are marked GP3 on the board, but also to some unused pins of the PCI Express connector, which I found is a bit unusual, but it's actually pretty handy. If you want to debug the ERC, you just take a board, solder on the right pins of the PCI like board and just stick it inside the device. You don't have to open it, and you just get serial output. So that's pretty nice. And this is an example of what the original non-free firmware serial output looks like. So it's not very clear what it does, but some of it can be figured out. Like if you start typing on the keyboard, you'll see the keystrokes appearing in some strange format. So yeah, we could try to understand what this actually means, but there's yeah, not much interest in that. And so these on the right side are the parts of the schematics that show the connection to the embedded controller serial ports. And the photo on the bottom right is the actual controller on the board. So it's actually the one on top, which has 4 pins and that you can easily solder to. It's actually on the side of the board that's facing the screen. So if you just remove the top of like the plastic part, you can just solder some wires in there. And there you go, you have serial output from the embedded controller. So that's nice, but we still need to flash our own firmware. So how to do this? Well, we need to access the internal memory, and it's mapped through a controller that is called the XBus interface, and it takes some specific commands to access the internal memory. So that's great, but this controller can be accessed from the 8051 CPU, but we cannot use it because, of course, we're trying to write its firmware. So how do we access this controller from outside the CPU? Well, there are essentially 2 solutions. One is called index.io, which is something from the controller itself, like some controller that allows accessing the internal memory layout of, like essentially the internal memory, including the controllers from the host, so using LPC. This approach could work, and actually there is an implementation of it in the Chrome OS version of Flash ROM for another version of these chips, but essentially the protocol remained the same. So I tried to use this at first, but it turned out the firmware would explicitly disable that. There is like a register that you can write to just disable this feature, and the non-free firmware does it. And since LPC has to be accessed from the host CPU, it implies that the firmware has already started, like the embedded controller firmware has already started, and it has already locked this. So unless we're going to like put some connectors on the LPC lines and use it this way, which is not really, it's not really a comfortable thing to do. So I looked for another way, and there is actually something called the ENE debug interface, which is essentially the SPI protocol with some specific commands. And this allows to access the internal memory space of the embedded controller as well. So this debug interface is exported on the keyboard pins. So all it took really was to solder some wires on the keyboard connector, which is not that easy because the pins are actually pretty small, but it's doable. And there is an application note on the embedded controller that explains how you can communicate with this interface. So I wrote up Flash ROM support for it, which is still under review and might stay under review for some time, but we'll see about that. Anyway, the code is ready, it works. So from this, I was able to write the internal memory of the embedded controller. So now it was time to do some early investigation about the board itself, like how I would write software and how I would bootstrap like a free firmware for this. And to do this, I found some cheap boards online like this, which just have some pins exposed and allow you to solder the embedded controller chip that you can also buy separately on that. So I did it. I think I bought like maybe 5 or 6 of them before succeeding, because it's LQFP 128 soldering, which is some very, very tiny pads, and those are pretty hard to solder right, and it actually took some getting used to. Yeah, sure.
You soldering it with an iron or with a hot air gun?
Oh, so question is, am I soldering this with an iron or with a like a hot air gun? Actually, with an iron, if you use, so the technique goes like this. You align the chip perfectly so that, yeah, all the pads match the traces on the board. Then you put some soldering on all the pads, like you make one big short circuit, and you try not to touch the pads so they don't move. And then you put a lot of flux in there, and you use some solder braid to remove all the extra solder that you have in there. And if you do it right and you do it like sufficient, as many times as it takes, you can remove all the extra soldering in there, and so you'd only have the pads properly soldered to the board. But it fails. It often fails, actually. So it took me some time to get this right. It turned out that the exposed pins are the ones from the keyboard controller that allow you to access the flash through EDI, so the ENE debug interface that I just mentioned. This actually allowed to write the flash ROM support more easily, because actually I could travel with this and just write the software as I traveled, which is more convenient than just having a laptop with you that you have to open all the time. So that was great, but there is no serial connector on this, and really nothing much other than the EDI connector. So it was kind of a dead end otherwise. I couldn't really bootstrap the code. I could know that it was running from EDI, but there is really no I/O or nothing interesting from there. So really, I moved on to using the main computer as development platform. So doing this, I started to get interested in the software parts, and starting with an early software bring-up. So first off, I had to learn about the 8051 instruction set assembly, which looks like this. So it's not actually very complicated. You only have 255 instructions. They're pretty well documented. The platform is so old that there is documentation about it all over the place. So really, it's not hard. And yeah, first off, I started by writing the bare opcodes with like a hex editor, which was a pretty fun thing to do. And with that, I could just enable serial and blink a LED. Oh, well, actually turn on a LED, because blinking is much more complicated. You have to use timers and all. But yeah, essentially turning on a LED and setting up the serial controller, which is not so hard either, and just printing hello world. So this went pretty well, but this is not a proper development base, of course. Nobody wants an embedded controller firmware that is written by hand using bare opcodes, and I'm not going to get very far with that approach. So for proper development based, of course, I decided to use the C language for writing the firmware. But it's an 8-byte microcontroller with a very strange memory layout, so there is no GCC support for it. But instead, there is another compiler called STCC, which is a small devices C compiler that brings some specific extensions that are required to support this. Essentially, well, how to deal with the different memory layouts, like different memory spaces. This compiler has all the extensions, which are really qualifiers that you use before the variables, and that really tell it where it should store that data. So yeah, it handles the memory models. You can actually have some presets about where it will store each different type of variable, how it should use stack as well. And you have to remember that it's actually a very limited platform. You don't have a lot of memory for stack. You don't have a lot of memory in general. So yeah, this has to be done quite carefully. So this is nice. With this setup, I can build code that I hope does something, but it's really not enough to figure out what the entire firmware does. So it was time to get into actual reverse engineering. So the first thing to do is, well, static reverse engineering. That can be done with a tool called Radar True, which has support for the 8051. It's a bit broken. I should spend some time fixing it, but it's essentially there. So you can disassemble the non-free firmware if that's legal where you live. I'm actually based in Europe, so it's legal for me to do that sort of reverse engineering for compatibility purposes, which is what I'm doing. And of course, if you're in the US, this is not something that you are legally allowed to do. And there is also dynamic reverse engineering, which actually works a bit like serial ICE, if some of you remember that. So the idea is to run the non-free firmware in an emulator and to actually transfer all the I/O requests to the actual device so that you can control and see everything that's going back and forth. So the idea is to really trace all the I/O calls. And this sounds pretty simple, laid out like this, but it's actually not, because this controller deals with interrupts, it deals with timers and lots of things that actually conflict with running the firmware on an emulator, because you have to also somehow emulate the interrupts or forward some of them. So it's pretty complicated. The thing is, you actually have to run a very small firmware on the embedded controller to be able to do this forwarding of the I/O. And so because you're running your own firmware on the controller, there are some things you cannot change. Like you cannot say remap the memory, because your own software is going to get very confused if you do that. But on the other hand, if the non-free firmware is doing it, you have to find a way to say, okay, let's not do this, but let's pretend we've remapped memory, but we've actually not done it on the device for this reason. So it's actually pretty complicated, and it's not fully working yet, as in it cannot boot the laptop this way, but I'm moving forward. Yeah, and I hope eventually it's going to be able to fully to work, to properly work, to be able to turn on the device, and so that I can capture everything that the non-free firmware is doing. And this way, it's really much easier to understand all the different steps to, say, turning the device on or to entering suspend or anything like this. So the flow goes a bit like this. MU8051 is actually a tool that was written maybe more than 10 years ago, maybe something like 16 or 17 years ago. And I used this as a base and extended it to call the MU8051 device library, which is something I wrote that interacts with the embedded controller firmware. So something I call the MU8051 KB9012. And actually, just forwards the I/O request in a specific format through serial. So it's working well. I have some results and already have some stuff that I can use to write my own free firmware. So let's talk about it now, writing a free software EC implementation for this. So there are some constraints. I've mentioned that. It has to be written in C, of course. We have to be careful about the memory size program, because it's very limited. Also RAM and stack, which are very limited on this platform. And really, I want to make this really a flexible implementation for any 8051 embedded controller, because this is not an isolated case. There are various other manufacturers of embedded controllers that use this same microprocessor core. So it might, I think it's important to make this implementation as generic as possible so that it can be reused on other such embedded controllers. I want to make it GPL v3 licensed because I can, and and that's not all of us can do this, but I'm not tied to any company or anything. So I decided to go with GPL version 3, and I decided to call it the Origami Embedded Controller Firmware, so shortened Origami-EC, which is a flexible free software embedded controller firmware implementation for 8051 based platforms. So the architecture of the code is the following. It's not event-driven, because really having context switch and test and stuff like that is a bit too much to ask for this platform. So it's really just running with interrupts on the side, doing as little as possible, and a main like a main execution thread that essentially looks for events and handles them as soon as possible with some priority design. So this is not yet final. It's really work in progress, and I don't really know what I'm doing either. I'm learning a lot along the way, and yeah. So I'll see where this goes. Maybe this design is not really well adapted. I don't know. We'll see about that, but it's something to start with anyway. So to make it possible to port this code to other embedded controllers, I've decided to use some generic APIs and to have some specific implementations for them. So you have a part of the code that's very generic and that's common, and that will just call this API that each device or platform-specific code will implement. Yeah, in that way. So the current status right now is I have console working with some nice commands that I can use to debug, like turn the LEDs on, turn the fan on, or anything like this, which is yeah, it's actually pretty fun and pretty useful for like debugging, stuff like that. LEDs are working, buttons and switches. That's all very trivial because it's really only GPIOs. So once you've written the GPIO stack or implementation, it's pretty easy to get those working. And it's actually pretty close to powering the laptop on. Following the power sequencing diagram, I was able to start some of it on. It's still not displaying anything, but like the fan is on, and I can see stuff that, yeah, doing some funny noises and all. So I'm suspecting it's doing something. Yeah. But yeah, a more reliable way to judge that would be to install coreboot on this, get early debugging, and see if boot block shows up or not. And that's what I'm going to do. And it still needs some work to get the initial power sequencing right, but I'm confident it's going to work out, especially if I can get to this point with the emulator, so I can really see what the non-free firmware is doing in what order. So it will be much easier to implement that, yeah, when I have this information available. However, it's not public yet. I'm still waiting to make the code public. It's going to happen probably over the next few months. Yeah. So this is actually the roadmap for the project. First thing is to turn the damn thing on. And when I've reached that, yeah, I'll probably consider cleaning up the code and making it, yeah, like a proper public version. The next thing is communicating with the host, so through LPC. There are some challenges in that. I don't really know much about LPC, so I'll have to learn a bit about it. But that's okay. It's going to be an interesting experience. Then also adding support for the keyboard and the various peripherals attached to the embedded controllers, so battery charging and all of the stuff that the embedded controller is actually supposed to handle. And of course, when all of that is done, we can get into the more complex stuff like advanced power management, so suspend and resume, which I suppose is not that, yeah, really not that trivial. And also look at EC power saving, so essentially getting the embedded controller to be a bit more optimized regarding its own power usage. Some stuff has to be discussed, especially the protocol to use between the EC and the host, because the protocol that the initial non-free firmware implements was not actually fully figured out. Like some parts of it are known, but some other are not. So yeah.
Is the protocol similar to the ThinkPad?
So yeah, is that asking whether the protocol is similar to the ThinkPad ones? Actually, I don't really know. I didn't really take a look at the protocol of the ThinkPads, but maybe you can tell me if I show you logs or something. Yeah, I haven't looked at this very much, but either way, the question of what protocol to implement in that free firmware will have to be raised eventually. So we could either decide to implement something that matches the non-free firmware protocol, or to go with something else, maybe like the Origami-EC that has its own protocol. Yeah, we could probably use this one as well. So why not? And also the question of how to install this firmware, because as you've seen, I went through great lengths to reflash the internal firmware. And we have to figure out an easier way to do this. And there is probably one, because Lenovo is likely shipping updates of this. So there is probably, I believe there must be a way to disable the index IO limitation. The fact that the firmware is disabling it explicitly. There must be like some command to send the EC to tell it, okay, let's enable it again, so that you can use this to reflash its internal memory. So something like this has to be figured out, and it's probably somewhere hidden in the non-free firmware. So if I look at it like real close and real deep, I'll probably end up finding something like this, some special command that triggers this sort of behavior. Because really, we can't expect any user to just solder wires on the keyboard connector and to use external hardware to reflash it because it's SPI. So yeah, really, an easy installation process has to be like figured out. Yeah. So the project itself will be released publicly, in some month, and it's going to come out with some associated infrastructure. So essentially, repository, some documentation about all the stuff I've mentioned with more details, of course, and installation instructions when they're available. But also a mailing list to coordinate development if some of you are interested in helping me with this. Any help is really greatly appreciated. Also releasing these, the tools that I use for emulation, so the stuff I wrote for this. And once again, contributions, either technical or not, are welcome. And that's it for this presentation. Thanks. If you have questions, I'll be happy to answer them now.
Have you tried to use IDA disassembler for the original firmware? Because as far as I remember, IDA has support for 8051,
okay.
And it can just it shows you the complete firmware flow.
All right. So question is whether I've tried IDA. Well, I don't use IDA because it's non-free software. So essentially, question is no, I have not tried it, and I'm not really interested to try it because well, actually, the very reason I'm doing this is because I want free software on my laptops, and I try as much as possible to only use free software in my development flow. So if I can avoid IDA, I'll avoid it as much as possible. And Radar 2 actually has decent support for 8051, so it might not be as good as IDA, especially given like the graphical representations of the code and stuff like that. But frankly, it's good enough for me, and I don't know much about ADA, so don't really want to learn for the occasion.
Okay.
All right.